Now this figure 20-10 from Stallcup's Electrical Design Book, Volume 2, covers the requirements for primary only protection where the transformer is rated 1,000 volts or less in accordance with NEC 450.3b and Table 450.3b. Now, since the current is 9 amps or more on this primary, we can size at 125% of the primary's full load current, and if that percentage of 125% doesn't correspond to a standard overcurrent device, then the note 1 and the table below the table would allow you to round up to the next size above 125% or round it down. It wouldn't make any difference as long as you could energize the overcurrent device of the primary side and it wouldn't trip due to the inrush current. Now, when we basically review this transformer here, we have the primary overcurrent device, as you see in the illustration, at 125%, and the conductors at 125% to supply that primary. Then on the secondary, we're making a 10-foot or 25-foot tap, say. And we're wanting to size that overcurrent protection device in the primary side where the transformer is rated, as you see in the illustration, 20 kVA, 240 volt primary, and a 240 volt secondary. And then, of course, you have the EMT being used as an equipment ground from the panel board to the transformer in accordance with 250.118. You have the main bonding jumper size. You have the grounding electrode conductor size connected to the grounding electrode system. Then you have the system bonding jumper sized properly in accordance with 250.30A1, 250.102C, and 250.66. The grounding electrode conductor is basically sized and determined in 250.30A5 and connected to the electrode, which is in 250.50. But you have your sections here to complete the complete installation when you start the design. But now, reviewing our step 1 and the boxed in information with the title head, finding the overcurrent protection for the primary side of the transformer. Step 1, full load current equal kVA times 1,000 divided by the voltage. So you have a 20 kVA transformer times 1,000 divided by 240, 83.3. Now, notice in step 2, we apply what 450.3b instructs us to do by using those percentages found in table 450.3b based upon the transformer's primary current being over 9 amps, which is 83.3. See, so we can select 125% based upon this value. We come up with 104. Now, the engineer or electrician in step 3 can apply our table 450.3b along with note 1, select the overcurrent device in accordance with table 240.6a, which lists the standard sizes in that table. And notice it was decided in step 3 to round it down to 100. Usually it would be about 105.6 or something like that before they'd round up usually to 110 or 125 to select the overcurrent device. So it's rounded down here, but you could round up to 110, but that's an unusual size and sometimes will cost you more money than the 100 amp. And then again, you can place that 100 amp, in a 100 amp disconnect, say, or a 100 amp circuit breaker, whichever. If you use a disconnect, that's 100 amp fuses. If it's a circuit breaker, a 100 amp circuit breaker. So the solution basically says the overcurrent protection device in the primary side of that transformer should be rated at 100 amps by the solution by rounding it down. So this figure 20-10 just basically shows the procedure for sizing the primary overcurrent device only. You're putting it in the primary to 125%. It's 1,000 volts or less rated transformer. And we're following the requirements of 450.3b and table 450.3b. And that's what our figure 20-10 is illustrating. The transformer has a primary current of 9 amps or more, and we're using the 125% times that primary current of 83.3, and we can either round it up to the next size protective device or round it down to the next size protective device listed in our table 240.6a in the NEC.